Dhruva here. I'm an engineer at Uber. Today, we'll walk you through our work on embeddings at Uber. Here is the agenda for today. We will start with how Uber uses machine learning. Then we focus on embeddings and then how embeddings are trained using the two-tower architecture. And then we will discuss about the challenges we have faced while training these two-tower models and the solutions that we innovated and also we incorporated from the industry. And we'll also look at the architecture for embedding versioning and online serving of these embeddings. Finally, the impact that we had across Uber. Let's just first start with ML at Uber. Machine learning plays a critical role at Uber, supporting both our internal and external facing applications. For example, we use ML for marketplace efficiency, helping match riders and drivers and setting prices and dispatching trips. ML is also crucial for our safety and risk systems, where it powers our fraud detection and incident prevention systems. Additionally, personalization and recommendations are major areas where we deploy ML to improve user experience, like in Uber Eats home feed. Uber Eats home feed ranking. One of our key models is Uber Eats home feed ranking system, which is the first interaction for 95% of our users. Most orders on Uber Eats start on this feed, and we have a very limited space to show the most relevant stores and items. It's critical that we show the right recommendations quickly because the feed ranking has direct impact both on user satisfaction and our business outcomes. And we faced two major challenges that drove us to adopt embeddings across Uber. First, our retrieval systems, retrieval models were not efficient. We needed to retrieve the best stores from thousands of options in under 50 milliseconds. And second, our existing solutions, the deep matrix factorization, that is DeepMF, couldn't scale with Uber's growth. It required over 1,000 city-specific models globally and consumed a huge amount of compute resources. And we have seen the performance started degrading as we scale. We adopted embeddings as a long-term solutions to these challenges by upgrading our ML platform, Michelangelo, to make embeddings as a first-class citizen at Uber. That is, the advantages with embeddings are it offers a better performance and also has lower compute needs. And these embedding systems can be scaled at Uber growth. We first applied embeddings to replace our deep matrix factorization model in Uber Eats home feed ranking. This allowed us to retrieve personalized stores in under 50 milliseconds and significantly improve the speed and accuracy of our recommendations. With this success, we built out the entire embedding infrastructure that could be scaled, reused, and extended across other parts of Uber business. Let me briefly explain what embeddings are. Embeddings are these condensed vectors that capture the essential information of an entity. We use embeddings to represent several entities at Uber, such as eaters, stores, items, grocery stores, and geolocations, places, etc. Embeddings have become even more popular recently with the rise of generative AI in the RAG systems. Further, embeddings allows us to replace a large set of features with compact representations, making them perfect for downstream ML tasks like clustering, ranking, and personalization. At Uber, we wanted to build this large-scale embedding generation system to produce embeddings for various entities across Uber. Today, we will focus how we generated embeddings for two key entities, that is, stores and eaters on Uber Eats. And these embeddings form the foundation of our recommendation systems, both in our first pass ranker and second pass ranker, to provide personalized experience for millions of Uber Eats customers. Let's just start with how did we train this embedding model, and also how did we generate these embeddings. To train our embeddings, we used two-tower embedding model, which is a standard architecture for recommendation system. It helps us to learn embeddings based on the user behaviors like clicks and orders. The model consists of two separate networks. One is a query tower, and then the other is the item tower. The query tower, in the case of Uber Eats, in this tower, we input eater-related information like what were their past reviews for the orders, their spending patterns, their orders, their past orders in the last 6 months, stuff like that. And the item tower, this tower handles the store-related information, like the menu, the store ranking, number of clicks or orders, and the pricing information of the store. On the right, you can actually see the architecture of the two-tower model. Each tower generates its own embedding, We then compare them with the similarity functions like dot product or cosine similarity. This lets us rank stores for each user based on the preferences and then interactions that they have done in the past. If we train this model correctly, the model should group similar stores and users together in the same embedding space. For example, we would expect all the Italian restaurants in a city to be clustered together. And similarly, users with a shared interest would be placed near each other in the embedding space. You can see on the bottom left that all the Italian restaurants are actually placed at one corner and then the Asian restaurants on the other side. Oh, and also I wanted to discuss some of the training challenges that we faced for training such a TTE model. Training embeddings at a Uber scale comes with significant challenges. One of the biggest challenges is the sheer number of users that Uber Eats have, millions of them. If we create an embedding, unique embedding for each user based on their user ID, the model would be too big to handle for Michelangelo. We explored several common solutions like hashing, hash tricks, bucketing of the users, but the most effective approach was to represent the users as a sequence of stores that they have interacted with, rather than embedding user ID directly. This drastically reduced our model size. Another optimization that we have done is we applied, we got inspired by this GPT-2 architecture where we share embedding weights between both the eater tower and the store tower. This compressed the model further while maintaining the accuracy. With these two optimizations, we achieved a 100x reduction in the model size, making it much more scalable without sacrificing any performance. Up next, one of the unique, I wanted to also discuss some of the unique challenges that are very specific to Uber. At Uber recommendations are location-centric. What do I mean by that? For example, there is no point of recommending a restaurant in Japan to a user in San Francisco. To handle this, we use spatial indexing, which is nothing but we convert the 2D coordinates into a single geohash. This allows us to fetch only the embeddings for restaurant around the user location. In order to integrate this information into model training, we sort the training data by geohash, so the eaters and the nearby restaurants are grouped in the same batch. This helps us to create this hard examples during the training, allowing the model to learn better and optimize more effectively. Another issue we faced is some popular restaurants get far too many orders, which can skew our training data and then also the training of the model. To address this, we applied the log queue correction inspired by Google Paper, which downsamples these overrepresented restaurants in each batch and thereby balancing the data set. Yeah. And then let's just discuss about the architecture. Here is the architecture on how the embeddings are used in the retrieval system. Let's just first start with the store embeddings. These are the information related to store doesn't change much. So we can compute these store embeddings offline at a weekly cadence and disperse into a search index. And the eater embeddings, these are computed online using our eater tower deployed on our online prediction service. So here is how the typical request goes through. For every request, the query embedding can be computed on flight per request using Michelangelo OPS. And all we have to do is a dot product between the query embedding, which was computed on the fly, with the dot product of the query embedding and the millions of pre-computed item embeddings. Doing dot product at scale is a solved ML problem, as we can use sophisticated techniques like ANNs. Now, let's discuss about the another aspect of using embedding as a feature. Embeddings are powerful as they can be used as features in the downstream ML models. A feature is a data that has a predictive power that can be used as an input for models to make predictions. As we discussed before, embeddings have this predictive capability, making it an ideal feature to be used in downstream models. At Uber, we disperse our embeddings through our feature store palette. This makes it easy for other teams to access and use these embeddings in their own models with simple config. In our case, it is a two-line change. At Uber, embeddings are now used more than just for the retrieval task. They have been a core feature in many of our tier 1, tier 2 models like Deep CVR, which are key for our customer conversion and engagement. As these embeddings are reusable and servable through Palette, this reduces the redundancy and makes it easy to share embeddings as feature across teams within Uber. To fully integrate embeddings into our system, we introduce a new data type called embedding in Palette alongside other existing types like numerical and categorical features. We have also added support for common transformations that are needed on embeddings, like padding, filling missing values directly into Padlet to make it much more flexible so that other teams can use it off the bat. This approach has significantly improved the feature exploration and engineering at Uber, as we have found that one single embedding can often replace hundreds of manually engineered features and streamlining the model process. Impact. The TT embeddings enable us to replace us 1,000+ city-based models with one single global model. These embedding systems are more scalable, supporting millions of Uber Eats users, supporting multiple sessions, multiple locations, multiple cities. We also significantly decrease the time and the resources required for model training. Before, with our DeepMF model, we needed 200,000 core hours to train the model. Now we just train it in 4,800 cores, 4 hours per week. As the TT architectures are scalable, we were able to train on the longer data range, helping us to improve our optimizing metric, recall at 500 by 17%. And finally, I would like to take a moment to acknowledge the team behind this project. This work was a collective effort. It wouldn't have been possible without all their contributions. And yeah, that's it from me. And thank you. Yeah.